Yeah, I saw one on academic.
Yeah, something on academic leadership.
Yeah, leadership. Yes.
Karan, are you admitting the students?
Yeah.
Okay, a lot of them in the waiting room.
I think the live stream is already on because it's 3:31.
Okay.
Karan, just admit all.
I'm doing that, ma'am. I'm admitting everyone who's coming in.
Yeah, just admit all. So, Rijutha, I can see Ashwin from your classmates.
Hi, ma'am.
Hi, Ashwin.
How are you doing?
Good, good.
Hi, Ashwin.
Hi, Rijutha. Hi, sir.
I was muted, sorry. Hello, how are you?
I am doing well. How are you?
I'm good too.
Really nice to see everyone after a long time.
Yeah.
How's the situation there?
I mean, it never got really bad. So we still don't use masks and things like that. I mean, it's only in public transport that we use masks. But
That
I
was
think
pretty
it's
good.
getting worse now.
Good in the sense that I think if the cases are that low that you don't need to use masks, then that's good, I guess.
Yeah. I think, I mean, now in certain areas like Copenhagen, it's getting quite bad. But they're offering free testing for everybody. So you can just book a time and go get yourself tested.
Wow.
So they've handled it pretty well, I would say.
I think in India, we are half terrified of getting tested because the false positive rates are also quite high.
True.
Yeah.
So if you are tested positive, then I think you will be, I don't know what will happen.
Yeah.
Yeah, that uncertainty is what is more the cause of not testing.
Right. What my mom says is in her office, she's in the insurance company, so they have to go to office no matter what. They're saying that it doesn't matter what you have. If you go get tested, you'll get tested positive. So people are terrified.
I would say in India, the situation is better compared to in US.
Of course.
Yeah, US is bad.
Yeah.
Kumala, what time is it for you?
It's 6 o'clock, ma'am. How are you?
Good. So, Rijutha, somebody has given up sleep to listen to you.
Yeah, I'm flattered. I hope
telling
it's
you.
worth your time.
Oh, no. Hi, sir. How are you?
Hi, Komla. I'm good. How are you?
I'm doing good, sir.
Good to see you.
Yeah. I think I'll switch on the video.
I had just yesterday, I think I sent you a mail.
Hi,
I actually. Oh,
hello, ma'am. How are you?
I'm fine, ma'am.
I think we'll start in 5 minutes.
How many? There's some delay, Parul?
We're just waiting for participants to join in, ma'am. They are late. So we'll just wait for another 5 minutes. Sorry, Rijutha, we are keeping you waiting.
No, that's okay. I'm done for today with whatever I was supposed to do. So I started working at 6 today.
Oh, wow. You had a meeting, no, with your supervisor?
Yeah, it was about so she's in Germany right now, so it's all virtual meetings and whenever she finds time. So it was about the beam time that we are going to.
Ashwin is where now? Ashwin, where are you now? You're still in Gujarat?
No, I am back. I'm in Bangalore. I'm in ISC. So,
Okay.
yeah. Wait, that was Sheila ma'am, right?
Yes.
Yes.
How are you, ma'am?
Yeah, good.
Because your name is not seen and your video is also not seen. So.
No. Oh, maybe it's on a different screen for you, Ashwin.
Yes.
Probably.
Okay.
I see. So I came back to Bangalore about 2 years ago. Things didn't work out well in Ahmedabad.
Okay. So you are in IAC?
I'm in IAC. I'm doing astrophysics.
Okay. Under who?
Okay, so I'm working under Bishwajit Paul at RRI. So JAP program has the freedom that we can choose a guide in RRI, IAC, ISRO, or IIA. So I chose my guide at RRI.
Okay.
So yeah. So Rijutha, you're almost done.
I submitted my thesis on the
Congrats.
31st of August. I'm free now.
My God, I'm just starting.
You're next, Ashwin.
You see, I haven't written my first paper, and this man is saying, when is your thesis being submitted?
I still haven't published my first author paper. I mean, it's written, but it's stuck with my supervisor for now.
I haven't published my first any author paper.
Okay.
So we will get there.
Difficulties of all grad life, I could say.
Yeah.
Yeah.
In fact, what has happened is in IAC, we have this thing that at the end of second year, we have a comprehensive exam. So after that exam, you submit the thesis proposal. And then, things were supposed to take off. But anyway, so I'm working on a paper now, and that should add some credits. But still, my comprehensive exam is not done. So that's what I'm saying. You submitted your thesis. It's very nice. Yeah. So when are you planning on coming to Bangalore?
I mean, whenever it's easy to travel.
Acha, you're waiting to return then. So the work there is sort of done. You'll be going back after that?
Yes, I got a postdoc position here.
Wow, cool.
So I'm going to be here for some time.
Right.
You are in Denmark right now, Rijutha?
Yes.
How is the work going? Are you done with everything?
I'm done with my PhD work, but started with the next set of experiments.
Planning to continue there?
Yes, at least for a year.
Okay. Yeah. Good to see you.
Same here, ma'am.
Shall we start, Arun sir?
Yes.
Yeah.
All the best.
Good afternoon to all. Welcome to the inauguration of Physeeksee, the Association for the Postgraduate Department of Physics, St. Joseph's College, Autonomous Bangalore. Let me introduce myself. I am Arati Uni. I will be your MC for this evening. A gentle reminder about the instructions for the participants. Please switch off your microphone and video during the entire length of the presentation. Any questions regarding the lecture will be taken at the end. You can post them on the chat box on Zoom or either on the YouTube live stream. In between, due to any network issue, if you drop out of the Zoom meeting and you're unable to get back, please proceed to the YouTube live stream. We will start the event by seeking the blessing of the Lord Almighty with a short prayer. I request Alina to grace the occasion with a prayer song.
വിശ്വം നയിക്കുന്ന ചൈതന്യമേ നിത്യം നമിക്കുന്നു ഞങ്ങൾ ജ്ഞാനമാനന്ദമാത്മപ്രകാശം മനതാരിലകതാരിലുണരേണമേ മനതാരിലകതാരിലുണരേണമേ ഈരേഴു ലോകത്തിലുണ്മയിൽ വെണ്മയിൽ നിൻ പ്രഭാപൂരം ജ്വലിപ്പൂ ഈരേഴു ലോകത്തിലുണ്മയിൽ വെണ്മയിൽ നിൻ പ്രഭാപൂരം സംശുദ്ധമാക്കുവാൻ നീ കൃപയെ ഗണേ നിത്യം, നീ തുണയേ ഗണേ നിത്യം.
Thank you, Alina. I now invite Professor Parul Goel, our association coordinator, to deliver the welcome address. Over to you, ma'am.
Very good afternoon to one and all present here. On behalf of the Postgraduate Physics Department of St. Joseph's College, I extend a warm and hearty welcome to each and every one of you. It gives me immense pleasure to welcome Dr. Melvin Colasso, the registrar of our college. Thank you, sir, for taking time out of your busy schedule. You have always been very kind in accepting our invitation. Thank you so much. We are pleased to have amongst us our speaker for today's talk, Ms. Rijutha Jaganathan, who is currently doing her postdoctoral research from Aarhus University, Denmark. Rijutha is also our ex-student who did her BSc and MSc here at St. Joseph's. A very warm welcome to you, Rijutha. A very warm welcome to each and every one of you who has joined us today, Sheila ma'am and other teachers who have joined in, and all the students, our ex-students. We are pleased to have you all. The postgraduate physics department was started in 2010, and we have successfully completed 10 years this year. The PG Physics Association, Physeeksee, was inaugurated officially in 2017, and this is the fourth year of our association. This association was started with the vision to provide a platform to the students to showcase their talents and to nurture their skills for their all-round development. With the same vision in mind, we kickstart the activities of our association for this academic year. For the smooth functioning of our association, the office bearers for this academic year will be President Arati Unni from second year MSc, Vice President Karan Kinariwala from MSc second year, Secretary Vikrant Pulamati from MSc first year, Treasurer Shivani Nair from MSc 1, Spokesperson Agnes Rajiv from MSc 1. So this is our team official team of office bearers for this academic year. All the best to all of you. And I welcome you all to the association. Hope that we all have a wonderful and fruitful academic year ahead. Once again, a hearty welcome to each and every one of you who has joined us this afternoon. Thank you.
Thank you, ma'am. We have the registrar of our institution, Dr. Melvin Colasso, here with us today. I kindly request sir to speak a few words and officially declare the commencement of the activities of Physeeksee for this year.
Okay. Thank you. Dr. Arun Thampan, the postgraduate coordinator of the Department of Physics, Ms. Parul Goel, coordinator of the association, my dear colleagues, students, alumni, and guests attending the online lecture. Good evening to you all. Just yesterday, I came to know about this program, and I readily agreed to be a part of it. I was also reminded that I have been attending all the novel programs for all the last 3 years. And that was one reason why I readily agreed to be part of this program. And the other main reason is that I was very keen to listen to Dr. Rijutha Jaganathan, our alumnus, who has made us proud with all that she has accomplished so far. Thanks to the current situation, we are able to have a lecture live from Denmark. Not that it was not possible earlier, but we never considered it as an option. The current pandemic has helped us in many ways. Students will agree with me that you have saved a lot of time traveling to college, saved money on transport, buying new clothes, eating food outside, and so on. Imagine if this crisis had struck us just 15 or 20 years ago. We wouldn't have had any online sessions like this or classes, no interaction with friends, as there was no internet or smartphones then. It is always nice to see the brighter side of every situation. As the old English proverb says, necessity is the mother of invention. And times of crisis have led to some history's most important inventions. For example, in 1665, when social distancing orders were given, they emptied campuses throughout England as the bubonic plague raged, killing 1 million people in just 18 months. That time, a 24-year-old student from Trinity College, Cambridge, was among those who was forced to leave the campus and return indefinitely to his childhood home. This person, I suppose you know, is none other than Sir Isaac Newton. It was during the lockdown that he discovered differential and integral calculus, formulated a theory of universal gravitation, and explored optics, experimenting with prisms and investigating light. We also know the basketball game was developed during the recession of 1894 by Dr. James Naismith. We also know another important event in history, that is the 9/11 attacks. The iPod was developed within a few days after these attacks. The world wars themselves have nurtured many innovations and inventions. So, dear students, this is an opportunity for you to bring out the best in you, to be creative and innovative and come up with new ideas in conducting online activities for this association. I am sure you can come up with unique programs for this academic year, being the decennial celebrations of the department itself. And with the help of the ever enthusiastic staff of the department, I am sure that you will have some of the best activities conducted during the year. I leave you with this quote from Mary Shelley, an English novelist. Invention, it must be humbly admitted, does not consist in creating out of void, but out of chaos. I would like to thank Dr. Arun Thampan for giving me this opportunity. Have a wonderful evening and wish this association a great year ahead. Thank you.
Thank you, sir, for your words of wisdom. Now, I invite Dr. Arun Verma Thampan, the PG Coordinator of the Department of Physics, to introduce the speaker for the evening.
Very good afternoon to everybody. Apologies. This time my talkativeness, yapping as I generally call it, is a bit longer than usual. It gives me immense pleasure to introduce today's speaker, Rijutha Jaganathan, to all of you. Let me first put Rijutha's talk in context. As you know, with the numerous correspondence between all of you and us, now during your MSc here, as well as after you leave, the physics department keeps celebrating you, okay? Each of you are unique and have your own unique achievements. And when that joy is expressed through us, it becomes a myriad set of celebrations. When you message us saying you have been able to solve that pesky physics problem, it might be at the middle of the night that has been bothering you, or when you say one of the concepts that you had not understood from your high school days, you understood while studying a topic in MSc. During all that time, we celebrate you. We acknowledge, we have the joy that you experience. We too experience that. The digital platform, unlike during our MSc days, have kept alive the connection between teachers and students. And this means that we are able to celebrate you more often than earlier generation could us. Therefore, even after you finish the MSc course and leave, it's an awesome feeling when you are in touch and come back and tell us that you have found a huge amount of satisfaction when you see you have inspired a differently abled student as a school teacher, or when you come back and tell us that you have qualified MBA, or that you have qualified the NET lectureship, or obtained the NET JRF, or have qualified both NET and GATE. There have been the first time someone has done it, and these days these successes are being repeated, and every time it happens, and every time that it happens, it's an occasion to celebrate you. Okay? We are looking forward to many more such events of celebration of all of you students here now and who have been here before. Right? So the PG Physics department turned 10 this year, And coincidentally, we have one of our students complete her PhD requirements and moving on as a postdoc. Okay, so that's an occasion for celebrating you, right? So Rijutha Jaganathan is here, currently a postdoc at the Center for Interstellar Catalysis, and she completed her BSc and MSc from St. Joseph's College, Autonomous. She was in the 2011-14 PCM batch for BSc and was the best outgoing student that year from science. Following that, she completed her MSc in our 2014-16 batch. She was on a DST Inspire scholarship. Included in her bio, okay, is the following information, which I think it is sort of consequential in starting her future course. She did her MSc dissertation project on hydrogen deficient stars with Dr. Gajendra Pandey at IIA. Subsequent to which, she spent several months at TIFR under the VSRP program, in which she was trying to map molecular hydrogen in the interstellar medium using hydrogen fluoride as a tracer material. Okay, so this is part of a multidisciplinary field called astrochemistry. Multidisciplinary. Please note that. I'll come back to it. Okay. This project was the project that she did was with Dr. Bhashuti Mukherjee. Okay, multiple sentences are hidden under the next sentence, and she says that after this she joined the surface dynamics group at Aarhus University, Denmark, in September 2017. There was a lot of hard work behind those months. For a PhD, she did her PhD under Professor Liu Honecker. The PhD position was as part of a fellowship from the Marie Curie Innovative Training Network and was under a European collaborative effort called Europa, okay, which is spelled as EUROPAH. Okay, the PAH stands for polycyclic aromatic hydrocarbons. So her thesis work, as she will be detailing in her talk, involved doing material science, surface science techniques, that is surface science techniques to model the past in ISM. Okay, so it's a truly multidisciplinary approach. She used surface science techniques to study the interaction of various PAH molecules with the H atom, leading to small molecule formation. In particular, she looked at the effects that the shape and size of PAHs have on interaction. Okay. She has used and have had to learn on the go a variety of tools in material science like scanning, tunneling, microscopy, X-ray photoelectron spectroscopy, and temperature programmed desorption with mass spectroscopy. She even learned lathing. So as part of her thesis work, she has had to travel to other European nations as well. The keyword here is travel again, which I will come back to later, to collaborate. So notable among her collaborations is one with the Alexander Thielen's group at Leiden Observatory for theoretical results, and Jos Women's group in Radboud University for the experimental spectrum. Currently, she has submitted her thesis and is expecting the defense soon. And in the meantime, she has moved on as a postdoc with her thesis supervisor, Professor Liu Honecker. Sorry, I think I've okay. See, the impressive part of Rijutha's achievement is her ability for multidisciplinary studies. In between all the hectic material science she has been doing, she has also regularly contributed to writing travelogues. Okay, remember, I mentioned travel sometime back. Okay, she likes to travel and write about it. She has been writing for Deccan Herald for quite some time, and she reviews historic monuments. These writings she used to do even during her college days here. She also has a blog. It's an esoteric dish of her myriad interests. will let her tell you about it. She has fittingly combined the education she had in BSc, PCM in our college, along with language skills she learned from Professor Cherry and Alexander and colleagues of our English department, and definitely created a polyamorphous compound of a training here. With no more ado, ladies and gentlemen, here is the soon-to-be Dr. Rijutha Jaganathan. Rijutha, over to you.
Thank you, sir, for that really amazing introduction. I'm a little speechless. I might need a few seconds to hold myself together. So I'll start sharing my screen, I guess, in the meanwhile. Okay, can someone just quickly tell me if you can see my slides full screen?
Yes, Rijutha.
Yes.
Okay. Thank you, Arun sir, again for the really moving words. Okay, so today I'm going to be talking about bringing the interstellar medium to the lab. So just quickly, like most of you who have tuned in today, I did my bachelor's and master's at St. Joseph's College. So my bachelor's was PCM, and my master's was, of course, physics, with these wonderful people that you also get to learn from. And then, of course, I got to spend a few months with Dr. Bhaswati Mukherjee at TIFR as a visiting student with her. And this is where I sort of got really interested in this interdisciplinary field called astrochemistry. And of course, TIFR has a great campus, so it was really a great place to be for the few months. Then I came to Aarhus for my PhD. On the left is a photo of the beautiful campus. So Aarhus University often features on this list of most beautiful campuses in Europe. And on the right is a picture of my group, and the person with the crown is my supervisor, Liu Honecker. And I've had a really good group here to work with. And of course, as Arun sir mentioned, I was a Marie Curie scholar as a part of a European Union funded training network called Europa. So it actually consisted of like 16 PhD students and their supervisors, and spread across universities across Europe. So for a quick geography lesson, this is Germany, this huge big country, and Denmark is this tiny country here, and Aarhus is here. And I did a little bit of work at the Radboud University, which is here, and the Leiden University. Okay, the person circled is Xander Thielens, and he is one of the pioneers in this field, and you will come across his book, The Physics and Chemistry of the Interstellar Medium, if you ever get to study astrophysics. And so I got to work with him, and my first paper is published with him, so it's a big deal for me. I don't know why my slides are moving so quickly, so I'm just going to check that. Sorry. Okay. Again, I'm going to ask you, can you see my screen?
Yes.
Okay. So right now, I've decided to take up a postdoc position at the Center for Interstellar Catalysis with my PhD supervisor, Liu Honecker. And this is actually quite an interdisciplinary center. And I'm going to get to work with Dr. Harold Lennartz and Evine van der Schut, who are both at Leiden and are stalwarts in the field of astrochemistry and laboratory astrophysics. Just a side note that memes have helped me survive through the PhD journey. So wanted to have one there. Okay, diving right in, what is the interstellar medium? It is literally the space between the stars. So on this screen, everything that is black is the interstellar medium, the space between the stars. But the interstellar medium is not uniform. It's made up of clumps of material here and there. At places, it's quite cold and dense. And then at some places, it's quite tenuous and really hot and warm. So it's not uniform. So there are a wide range of densities, temperatures, and pressures. Okay, so it's not uniform and neither is it empty. It's made up of two components. So you could have...
Rijutha, seeing your screen changing. I don't know if it is only me. Can somebody else?
Yeah, the screen is stuck on the main page.
I think it's frozen. I think the screen is frozen.
Oh, okay. I can stop sharing. So I've stopped sharing now. Okay. So do you see that the ISM is not empty?
Yes, yes.
Yes.
And now can you see the ISM, the space between the stars?
Yes.
Yes, yes.
Yes.
Okay, so I guess I'll start again from here because I want this to be quite clear. I have to pin myself maybe so that... Okay, sorry for that. What is the interstellar medium again? It's the space between the stars. So on this screen, everything that is black is the interstellar medium. So anything that's in between the stars. The interstellar medium is not uniform. So it's made up of clumps. It's made up of a wide variety of densities. So it's not uniform. You could have a region which is cold and dark. And then you could have another region which is really hot and tenuous. So it has wide variety of pressures, temperatures, and densities. Okay, the ISM is not empty either. It's made up of two phases. It can have gas, and the gas is dominated by hydrogen. So there's a joke about the astronomer's periodic table, which just has hydrogen and helium, and everything else is metals for astronomers, which is fair enough because in the universe, 75% by mass is hydrogen, followed by helium, and then a small percentage of the other elements. We can then have the dust phase or the solid phase, and it is called dust. It's just like the dust that we are familiar with. So the dust can be of two types. It can be silicate dust and it can be carbonaceous dust. So the silicate dust is analogous to the sand on the beach, and the carbonaceous dust is analogous to when you burn organic matter, the soot that is produced is carbonaceous, and it's quite similar to the carbonaceous dust you would find in the interstellar medium. Okay, but I'm telling you that the ISM is not empty, but how do we know that? So for example, if there's a cloud in the ISM, and there's a star behind it, and the star emits some radiation, which the cloud absorbs and then re-emits, which we can record as a spectrum, and then we can find out what elements are in this cloud or what exactly is in this cloud. So to make that clearer, suppose you had the superpower to get out of the Milky Way galaxy and look at it edge on. In the optical region, this is what you would see. So you would see most... Did I continue? Okay, I guess I continue. So if you could look at our galaxy from far away, in the optical regions, this is what you would see. You would see emission from the stars, and then there's a lot of this dark stuff that you think is probably empty. But then if you had the superpower to wear infrared goggles and look at the same view, you would see this. So whatever appears dark in the lower panel actually lights up in the upper panel when you look at it in infrared. So just an analogy on the left, so that's a cat in the optical, when you look at it in the optical region, and then when you have infrared goggles, that is what the cat looks like. So it's a similar thing. Just to make sure, am I audible and are my slides changing?
Yes, they are.
Okay, great. Okay, again, this is, suppose we can see this galaxy in very different wavelengths, and then you can trace different material in the galaxy when you look at different wavelengths. And this is how we know from the mid-infrared, you know that there's dust. From the radio region, you know that there's atomic hydrogen, and you can do similar things. I'm just going to change my pointer to a laser pointer. Okay. So the ISM is not empty. So till date, about 204 molecules have been discovered in the interstellar medium. But these 204 molecules are made up of just 16 elements. So as you are familiar, the periodic table actually consists of more than 100 elements. But the molecules discovered in the ISM so far consist only of 16 elements. So I guess it's kind of fair that the astronomer's periodic table has hydrogen, helium, and metals. And then, of course, as expected, molecular hydrogen is the most abundant molecule in the universe. So now the question is, I just told you that the interstellar medium has varying density, has varying pressure, can be very cold, can be very hot, has all these different regions, these different conditions. So how do these molecules form? So chemical reactions in the interstellar medium can be, again, of two types because we have two phases. So the reactions can take place in the gas phase, or they can take place on dust grains. So let's look at how the most abundant molecule in the universe, molecular hydrogen, actually forms. So you're going to tell me, okay, you just told me there can be gas phase reactions, so molecular hydrogen can form in the gas phase. Okay, so we could have two-body collisions where you have two atoms of hydrogen colliding with each other to form a molecule of hydrogen. But every time a bond is formed, there's some energy that needs to be released. Now, molecular hydrogen is a non-polar molecule, which means it has no permanent dipole moment, and hence no electric dipole allow transition. Put simply, it doesn't have the means to get rid of this energy quickly. So what happens is that the molecule just breaks apart into two hydrogen atoms again. Okay, what about three-body collision? So here we could have three atoms of hydrogen coming together to form a molecule of hydrogen. And then the third atom takes away all the excess energy. Okay. This is a very highly probable reaction in the Earth's atmosphere. But what about regions of the interstellar medium where the densities are really low? So when the densities are really low, the probability of three atoms of hydrogen actually meeting each other and forming a molecule are pretty low. So this reaction is going to be quite inefficient in like very low density regions of the interstellar medium. So there could be a third type of gas phase reaction, which is the ion neutral reactions, where an atom of hydrogen can react with an ionized hydrogen to form molecular hydrogen. Now, this reaction rate depends on the abundance of the ions, and it's not easy to make hydrogen ions in all regions of the interstellar medium. Hence, again, this reaction is not efficient everywhere in the interstellar medium. But however, these reactions could have played a really important role in the early universe, where there were a lot of hydrogen ions. So gas phase reactions don't seem to be efficient enough to explain what's happening or explain all the hydrogen we see in the universe. So we end up with a situation where we need tinder for the hydrogen atoms or for any atoms. And Van de Hulst in 1949 came up with this idea that maybe dust grains can act as the tinder for hydrogen atoms. So basically, the dust grain is where hydrogen atoms come to find each other. So you would have two atoms of hydrogen meeting each other on the dust grain. First, they sit on the dust grain, then they meet each other, and then they can give away the excess energy to the dust grain and then leave the surface as a hydrogen molecule. Happy ending. But there are regions of the interstellar medium which are called photodissociation regions. Yes, fancy term, but simply what it means is in these regions, UV photons dissociate molecules. And these regions are basically boundaries between hot regions and relatively colder regions. So this image here is of the Orion Nebula. And this is a really hot region. And this region is hot because there are really young stars here which are pumping radiation into this region and ionizing everything that's here. And then here we have a molecular cloud, which is a very cold and dense region. And then in the photodissociation region is basically a region of transition between these two regions. So why are these regions interesting? It's because in these regions, as the name says, the photons dissociate all the molecules, including molecular hydrogen. And yet, astronomers tell us that there is a lot of molecular hydrogen in these regions. So, which means that there must be a really high formation rate. To give you an analogy, so we basically have a bucket with a hole in it, and the hole corresponds to the destruction of molecular hydrogen by the UV photons. And we are trying to fill up this bucket, and we are saying that hydrogen forms on dust grains, right? So to keep this bucket full, we need to have the rate of formation of hydrogen to be much higher than the rate of destruction. Now, the problem here is that the dust grain reactions are pretty inefficient in photodissociation regions. And how do we know they're inefficient? We know that from simulations, we know that from laboratory data, that the dust grain reactions are not as efficient as required in these regions. So basically, we need a second route to form molecular hydrogen. And then interestingly, in 2004, some astronomers saw a correlation between emission from a group of molecules called PAHs. Don't worry, I'll explain what PAHs are in a moment, but they saw a correlation between PAHs and H2 emission. So they came up with this model where they said, okay, maybe PAHs, this group of molecules, play some role in the formation of molecular hydrogen in these regions. Okay, so what are these PAHs? Polycyclic aromatic hydrocarbons. They are nothing but organic molecules made up of carbon and hydrogen. They can be pretty big. So you could have a molecule with 100 carbon atoms or 200 carbon atoms. So they're basically like transition zones between small molecules and dust grains. So they're smaller than dust grains, but larger than molecules, the small molecules in the interstellar medium. So here afterwards, I'm going to call them PAHs, and this is what I mean when I say PAHs. Okay, they are not exotic molecules. You're all familiar with them. PAHs are formed whenever there's incomplete combustion of organic material on Earth. So basically, they're there in your vehicle exhaust. They're produced when you burn something in the industry. The black stuff when you overdo your toast consists of these PAH molecules. When you make a kebab or a paneer tikka, the black stuff is again these molecules. So these are molecules you are familiar with. They just have a very long name, but let's call them PAHs. So how do we know that they are in the interstellar medium? So every molecule has its signature spectra, and PAHs have their signature spectra in the infrared region. And then, so the complication is that in the infrared region, you only see signatures that represent a family of molecules and not a particular molecule. So for the PAHs, you see a CH stretch or a CC stretch. So you don't know what exactly the molecule is, but you kind of know it's an aromatic ring, or it's an alkyl group, or you can sort of make out what family it belongs to. So this is the IR spectra for the Orion bar that I showed you just a few slides back. This one, this region, and you have this beautiful IR spectra. And this has actually been seen along sightlines to most galactic and extragalactic sources. So the consensus now is that PAHs are ubiquitous and they are quite abundant. So the recent estimate is that about 10% of the galactic carbon is locked up as PAHs. Okay, what we know so far. So far I've told you that there is something called the interstellar medium, that is the space between the stars. It's not empty, it's not uniform. There is quite a complex chemistry in the interstellar medium because we see 204 molecules. And then I told you that there is a special region in the interstellar medium called the photodissociation region, where UV photons dissociate all the molecules that form. And then we looked at how molecular hydrogen forms in these regions. And then the conclusion was that we need to have an alternate mechanism other than dust grain reactions to explain the observed abundance of PAHs. And then we looked at astronomical data which showed a correlation between emission from these molecules and molecular hydrogen, and the postulate that maybe these molecules, the polycyclic aromatic hydrocarbons with the very long complicated name, help in H2 formation in the interstellar medium. Okay. So now that we know that, what do we need to find out? So we need to find out what is the reaction rate for this reaction. How efficient is this reaction in the photodissociation region? So we have to basically find out, okay, does this actually help explain the observed abundances of molecular hydrogen in the photodissociation regions? And then another question is, what happens if I change the shape, or if I add some extra atoms to this PAH? How does this change the reaction rate? How does this make the reaction more efficient? Does it make it less efficient? Does it lead to the formation of other small molecules? And that is the question that I tried to answer in my PhD thesis. So I'm very proud of my PhD thesis. It's almost like a baby, and hence the picture. And this is one of the questions I try to answer in my PhD thesis. Okay, so we looked at what we know so far, what we need to find out. So how do we do this? You could be an observational astronomer, go back to the telescopes, find more correlations, or look at more data, collect more data about PAHs or small molecule formation. You could do some theoretical modeling or simulations of photodissociation regions. But to do these simulations, you would need some inputs to your model, which you would, of course, get from astronomy, but you would also need more inputs from the lab of reaction rates. And that's where laboratory astrophysics comes in. So so you could study these processes in the laboratory. And that's laboratory astrophysics, where you sort of simulate what happens in the interstellar medium in your lab and study these processes so that you get some numbers that can then go into theoretical models. So ultimately, you need all three of these to understand what the role of PAHs is in the ISM. And they are quite interdependent, which is why I have these boxes overlapping. You can't have them independent of each other. So it is a highly interdisciplinary field. Okay, so how do we recreate the conditions of the interstellar medium in the laboratory? So I told you a few slides back that the interstellar medium has a wide range of densities, a wide range of temperature, a wide range of pressure. You can't recreate the entire interstellar medium in one setup. But what you can do is simulate certain regions in different setups. So for example, you could use high energy lasers to create really hot zones. You could use, you can produce shocks in the laboratory to simulate regions that have shocks. And then in our lab, what we try to do is simulate the photodissociation regions, because that's what we are interested in. And the photodissociation regions typically have a pressure of 10 to the minus 13 atmospheres. And temperatures ranging from 6 to 1000 Kelvin. And the relevant surfaces, like I told you, the dust grain surfaces could be graphitic, it could be amorphous carbon, or it could be silicate. So in the lab, we can go down in an ultra high vacuum setup. You can go down to 10 to the minus 11 atmospheres. And then we can access the entire temperature range from 6 to 1000 Kelvin. And we have a wide variety of relevant surfaces. So you can either, there are groups completely committed to making dust grains that mimic astrophysical dust grains. So you could have an astrophysical dust grain surface. So what we use in my lab is graphite, and I'll tell you why. So when you have ions, they're really easy, or they're relatively easy to study, because ions can be controlled with an electric field or a magnetic field. But I want to study neutral PAHs. So how do you study something that cannot be manipulated with an electric field or a magnetic field? You either have to embed it in a matrix, or you have to put it on a surface. So we go with the latter, where we put it on a surface. And the surface has to be, so an ideal surface is one which does not interact with the pH, right? Because you don't want your surface influencing what you're measuring. So you want something that has a minimum interaction with the pH. But so luckily for us, we can use highly oriented pyrolytic graphite, or HOPG, or sometimes it's just called graphite. And this is actually even a dust grain analog. So basically we can study what happens when PAHs are on dust grains. So we use HOPG. And this is where the surface science part of my PhD comes in. Since we're studying neutral PAHs on surfaces, we need surface science techniques. So on the left is a UHV setup called the big chamber, because it's big. And on the right is a UHV chamber called the green chamber, even though it's not green. And UHV is just ultra high vacuum. So we use mainly 3 different techniques: scanning tunneling microscopy, X-ray photoelectron spectroscopy, and temperature programmed desorption using mass spectrometry. And don't worry if you are not familiar with any of these techniques. I will give you a quick introduction as and when you need it to understand the data. Okay, so temperature programmed desorption is one of the main techniques I've used for most of the data I got for my PhD thesis. And instead of going on and on and on a little more talking about it, I'll show you a quick video explaining temperature programmed desorption, which we made recently in our group. So hopefully, I've embedded the video into the PowerPoint, so hopefully that works out. If the video freezes or something, please let me know. Okay, I can't get it to play. So I'm going to share another screen. Can you see the video? Could you see the video?
Yes, Rijutha.
Okay.
For 3 years, Rijutha has been a PhD student at the Department of Physics and Astronomy at Aarhus University. Today, Rijutha is going to collect data for one of the last experiments in her PhD before she submits her thesis. The experiment that Rijutha is going to perform today is called the temperature programmed desorption experiment. Rijutha starts with a clean carbon surface called graphite. This is the same type of material as is found in dust grains in the interstellar medium. On top of this sample, Rijutha will build up a film of molecules called polycyclic aromatic hydrocarbon. The objective of the experiment is to heat this film of molecules and measure the temperature at which they start to desorb from the surface of the carbon material and move into the gas phase. The desorption of the molecules into the gas phase will be detected with a special instrument called a mass spectrometer. This video will show and explain the equipment that Rijutha is going to use to perform the experiment. She begins by cleaning the sample by heating it to a very high temperature. The sample begins to glow red at the center of your screen when it reaches 900 degrees Celsius. Rijutha then has to move the sample into position inside the ultra-high vacuum chamber using the manipulation tools available outside the chamber. As Rijutha turns the handle, the sample slowly moves into position. First, Rijutha deposits the film of molecules by bringing the doser as close as possible to the sample surface. The molecules move from the doser onto the graphite surface. Because the tools inside the chamber operate in vacuum, it can sometimes be quite difficult to move things from outside the chamber. Once the film of molecules is prepared, Rijutha again moves the sample, this time put it right in front of the mass spectrometer. Eventually, everything is lined up, and Rijutha can begin the process of heating the sample to force the molecules from the surface back into the gas phase. As the sample gets hotter and hotter, eventually the molecules can no longer stay on the surface of the graphite and desorb into the gas phase. The desorption of molecules from the surface into the gas phase is detected by a special piece of equipment called a mass spectrometer. The mass spectrometer can not only detect when molecules arrive into the gas phase, but can also sort those molecules according to their molecular weight, to charge ratio. All of the species in the gas phase enter the detector at the same time. The detector uses an electric field to separate the species with a high mass-to-charge ratio from the species with a low mass-to-charge ratio. In this example, only the smaller molecules, those with a small mass-to-charge ratio, make it through to the detector. Rijutha has started the experiment, the sample is heating, and now she's waiting at the computer to see the signal coming from the mass spectrometer. The sample heats at a constant rate of 1 degree Celsius per second, so it takes about 10 to 15 minutes to run each experiment. Some of the data has arrived, and Rijutha and her PhD student colleague, Frederick, have a look to make sure that everything is working in the experiment. As the sample heats, the signal that reaches the detector and the mass spectrometer increases slowly with temperature, until eventually there are no more molecules left on the surface and the signal starts to decrease again. This gives a characteristic peak shape to each temperature program desorption dataset. The data that Rijutha is particularly interested in is the temperature at the top of this peak. The experiment is finished and it's time to turn off the equipment. Rijutha sits down at the computer to check that the data look correct. This is exactly the peak shape that Rijutha was hoping to see. As the temperature increases, the peak gets higher and higher until a peak temperature is reached and most of the molecules have desorbed from the film. Rijutha can now use the software to find that peak temperature and her experiment is complete.
Okay. I hope that was clear. Was there some problem with the sound?
I think it was fine. There was a slight background noise, but I think it was fine overall.
Okay. So I'll go back to sharing my presentation. So I hope you now understand what temperature programmed desorption is. Please let me know if, again, you can't see my slides changing or something. Can you see a beautiful molecule in the middle of the slide?
Yes.
Yes.
Okay, great. So we continue. So temperature programmed desorption gives us a mass spectrum of what is on the surface. So one of the first experiments that were done in my group was to study the interaction of coronene, this really beautiful symmetrical molecule, with deuterium and hydrogen atoms. So what they did was you have a clean graphite surface, and then you make a monolayer of coronene on top of it. And then you heat this up in front of the mass spectrometer, and what you get was those TPD curves that you saw, which can then be integrated to get a mass spectrum. So coronene has a mass of 300 AMU, and as expected, you have a really big signal at 300 AMU. If you want to know what the other small peaks around it are, ask me in the questions. Okay. Then we make another monolayer of coronene molecules on the HOPG or graphite surface, and this time we expose it to deuterium atoms. Okay, and then we do a TPD or temperature programmed desorption again, and this time this is what we see, the one in the lower panel. Now, what is surprising is that coronene has 24 carbon atoms, which means that you can add 24 deuterium atoms to coronene, right? And if you add 24 deuterium atoms to mass 300, you should end up with mass 348 because deuterium has a mass of 2. Okay, so why do we see masses above 348? Like 348 should have been the highest mass that we saw, right? And you can explain the presence of the higher masses by actually looking at not only a deuterium atom adding to every single carbon atom, but deuterium atoms actually exchanging with all the hydrogen atoms that are already on the coronene molecule. So what happens is, look at this inset here. You have so you have these carbon atoms at the edges having one hydrogen. You have a deuterium, which is in the yellow, coming in and attaching itself to the carbon atom. The carbon atom now has 4 bonds. Then you have a second deuterium atom coming in, abstracting away the hydrogen atom, and then you have leaving as a HD molecule, and then you have another deuterium atom, the third one, attaching instead of the hydrogen. So the difference between the last structure and the second structure is that the hydrogen is now replaced with a deuterium. And now if we look at it, so if we look at coronene with 1 extra deuterium atom, and then all the hydrogen atoms replaced by a deuterium atom, the mass is 360. And that explains why we see these large masses or masses greater than 348. But this is also interesting because this is evidence for the formation of molecular hydrogen via these reactions from PAHs. Okay, but I kept telling you about hydrogen. Why did we start doing the experiments with deuterium? Well, of course, if it was hydrogen that I used instead of deuterium, if a hydrogen replaced a hydrogen, the mass would still be the same, so you wouldn't be able to make it out. So of course, we're going to repeat these experiments with by exposing coronene to hydrogen instead of deuterium, and then we get this beautiful series of mass spectra. And I want to draw your attention to panel D, where you actually see that some of the masses seem to stand out. And by stand out, I mean that they have a higher yield than their neighboring masses. So for example, mass 314 corresponds to the addition of 14 hydrogen atoms to coronene. And this seems to be a really, there's a high yield, which means it's a more stable species, right? Because In mass spectrometry, a higher yield means it's a more stable species. And then you can notice that all the stable or higher yield species have an even mass, right? 4, 8, 10, 14, 18, 22, and 24, which is the fully, when you add an extra hydrogen atom to every single carbon atom. And then you can see that when you expose it to a really large amount of hydrogen atoms, the highest mass you get is 324, which sort of fits with our idea. 300 is the mass of coronine plus 24 hydrogen atoms. So that's 324, which is what we see. Now, with these stable masses, we can actually understand the reaction dynamics, right? And another thing that the temperature program desorption experiment directly gives you is the reaction cross-section. So this is a very, it's a quantitative technique as well, because you can plot the decay of the parent mass, which in our case is mass 300 for coronine, as a function of the D atom or H atom fluence. And it's a beautiful exponential decay that fits a first order reaction given by this equation. So you fit it with this, and one of the exponential parameters is the cross-section for addition of a hydrogen atom to coronine. So you can get that, and this is the value. The value is not important, but I want to make the point that you can get something quantitative out of this. If you want to get the reaction cross-section for the following reactions, like for the addition of the second hydrogen atom or for the abstraction, then you have to do some simulations. And they're generally kinetic Monte Carlo simulations where you kind of, put in, you try to get, you put in some parameters and try to simulate the mass spectra. And then out of that, you get reaction cross-sections for the following reactions. Okay, so you will find more details about the KMC simulations in this paper. I'm not going to discuss that here. Okay, so I spoke to you about the stable masses that we see when we hydrogenate or deuterate a PAH. So one thing we can do in the lab is to image these molecules or these stable structures to see how are the hydrogens arranged on this molecule. Why are they stable? Or, what is the structure that makes them stable? And the technique that we can use is scanning tunneling microscopy. And it's actually a quite intuitive technique. So, think about reading Braille. So you run your fingers across every single line, and then your head sort of makes up what each letter is, and then you know what that sentence reads. Right? So on the same way, in an atomic scale, consider a really sharp metallic tip that sort of scans over the surface on which your molecules are to create an image of the molecules. And the image of the molecules is actually a function of both its corrugation on the surface and the electron density. So what you get is a picture of the electron density on the surface, and which is basically then an image of the molecule. And I'm using the term image quite loosely, so it's not literally an image of the molecule. So here is an STM image of a monolayer of coronine. And you can see that there are two different regions here. There's an ordered phase here, and then there's a disordered phase here. And then looking at the ordered phase in close-up, you can actually see 6 different lobes corresponding to the 6 aromatic rings around the central ring. Okay, and then here is a close-up of the disordered phase, and it's a little more difficult to actually make out every single molecule, but you still can sort of see it. And the scale here is about 10 nanometers. So then now we have an image of the monolayer of coronine. So we expose it to hydrogen atoms and then image the surface again. And now the surface just lights up. So here you can see still a pristine coronine. It kind of looks the same as what we saw here. So you can see the 6 lobes around. And then we see a wide variety of structures. So let's start with the one here. You see that half the molecule is brighter than the other half. And here you see that there are 3 lobes rather than the 6 lobes that are in the pristine coronine. And then you see here, there are 3 lobes which are sort of linear. So the molecule is more linear here, whereas it's more, circular in the other 3 cases. And then what we can do is try to make structures that result with an electron density that looks like this. And then again, we have to ask our theory collaborators to do this because we can't do this ourselves. And then we can understand which structures are stable. So does it mean that a coronine with only hydrogen atoms on one side of the molecule is more stable, or a molecule that is curled up is more stable? And this is what we can do with STM. Okay, that was the work done in my group previously. And so then I came up with, or I wanted to know, what happens if we try to do this with a linear molecule like pentacene? So pentacene has 5 rings and it's a linear molecule, and it has what is commonly known as zigzag edges. So if you look at coronine, it doesn't have a zigzag edge. It has what is called an armchair edge because this part of it kind of looks like an armchair. And so pentacene has these zigzag edges, and it's quite interesting to understand how the reactivity changes when you have a zigzag edge instead of an armchair edge. And why is this important? Because we don't know, exactly what kind of what exact pH is in the interstellar medium. So we have to know how a wide variety of pHs behave. So pentacene is a linear pH. And then I wanted to look at pentacene quinone. So it's a linear molecule, just like pentacene, except now there are 2 oxygen atoms on the central ring. And then now that there are oxygen atoms here, the question is, can we form water through abstraction? So just like we saw that we can form molecular hydrogen by abstraction reactions, can we form water molecules through abstraction reactions? And I know whenever we think of molecules and how to make them, we typically think of, okay, if I want to make a water molecule, I need 2 atoms of hydrogen and 1 atom of oxygen, and I have to somehow get them together. So that's known as the bottom-up approach of making a molecule. But then you could also have a top-down approach of making molecules. So you could have water forming from a large molecule breaking down into smaller molecules. So this is something that I've tried to look at. And then, of course, I wanted to look at a PAH with a pentagon in the middle. So for example, this is corannuline. It looks a lot like coronine, except the central ring is a pentagon here instead of a hexagon in coronine. What you can't see here is that corannuline is actually a bowl-shaped molecule, whereas all the other 3 molecules I have here are quite planar. So then it's also interesting to see if, a bowl-shaped molecule behaves differently on the surface. Okay, so hereafter, it's going to be a quick highlights of my results. It's going to be, I'm not going to go into details, but of course, you're welcome to ask me questions about it later on. So what do we see for pentacene? So we do the same experiment that we did for coronine, where we put a layer of pentacene on graphite, expose it to hydrogen atoms, and then do temperature programmed desorption for varying exposures to hydrogen. Then again, you see that in panel C, we see that certain products with even number of extra hydrogen atoms seem to be stable. Okay, it's similar to what we saw for coronine. And then we see that it can be fully superhydrogenated. So pentacene has a mass of 278. And if you add, I forget how many, but if you add a hydrogen atom to every single carbon atom, you end up with a product with mass 300. And we see that you can add a hydrogen atom to every single carbon atom. And then we find the reaction cross-section, and we find that it's twice that of coronine. And this is experimental evidence for the fact that zigzag edges are more reactive than armchair edges. So if you had a PAH with a zigzag edge, you could potentially predict that it's more reactive than a PAH with an armchair edge. And then we collaborated with theoreticians at Leiden University to understand why we see these stable masses. And the results you can find in this publication, Kempisi et al., which came out earlier this year, and it's my first publication. So you will find details about the structures and why these masses are stable and why they're important in that paper. Okay. Then let's look at the pentacene quinone, which is one of my favorite molecules. It has these 2 oxygen atoms on the central ring. And this was quite interesting because if you see panel 2, as soon as we expose a monolayer of pentacene quinone to hydrogen atoms, it loses oxygen atoms. It also adds hydrogen atoms, to the pentacene quinone, but then it also loses oxygen atoms. So pentacene quinone has a mass of 308. And when you expose it to hydrogen atoms, you see that there are many more lower mass species rather than the higher mass species. So if we were only adding hydrogen atoms, you would only see the higher mass species, which is the case for pentacene, right? You don't see too many masses here, but you see a lot more masses which are greater than the parent mass. And then again, for pentacene quinone, we see that certain stable superhydrogenated or certain stable species are there, and they correspond to an even number of additional hydrogen atoms. So for pentacene quinone, we see that the 6, 12, and 18 extra hydrogen atoms are more stable. And then another surprise is that when you expose it to hydrogen atoms for a long time, you end up with pentacene plus 22 hydrogens. So basically, the molecule has lost both its oxygen atoms, but a hydrogen atom has been added to every single carbon atom. And that's this product with mass 300. It's the same product we see for pentacene, the mass 300. And then again, we find the reaction cross-section, and it's 3 times that of pentacene. So definitely having an oxygen atom on the PAH makes it more reactive. And then, of course, there's the indirect evidence for formation of an oxygen-containing molecule. So calculations for this are still underway. So we don't exactly know how the oxygen atom is abstracted. So hopefully, when we have the calculations, we will be able to say with certainty what's happening. Okay, next slide, if I can get there. I don't know why I can't get there. Okay, corannuline, which was the molecule with the pentagon in the middle, throws another surprise, and this was quite exciting for me, because so far we saw that it was the even number of hydrogen atoms that showed that were more stable. And then voila, for corannuline, you have a product with 17 extra hydrogen atoms that is quite stable. And of course, this kind of indicates that it has something to do with the pentagon getting hydrogenated. But again, we need calculations to definitely say what's happening, and these are also underway. Or we could do STM to look at what's happening. And then for corannuline, the fully superhydrogenated corannuline, or a hydrogen atom attached to every single carbon atom in corannuline, has a mass of 270. We see a little bit. So corannuline has 20 carbon atoms. So you can add 20 hydrogen atoms, and you get a product with mass 270. We see very little of it, and not really, it never dominates the mass distribution. So somehow it's not really very stable. Like, it's stable enough for us to detect it, but it's not formed in large amounts. So this was another really interesting result. And the reaction cross-section for corannuline is 5 times that of coranine. So just replacing the central hexagon with a pentagon makes it 5 times more reactive. Okay. So why do we do what we do? Firstly, because it's fun. Isn't that why we all do what we do? And then secondly, like I explained before, we can use these reaction rates in astrochemical models. So a lot of people actually spend some time modeling particular regions of the interstellar medium, like the photodissociation regions. They take inputs from both observational astronomers and experimental physicists. and create these large-scale reaction networks and models. And so what we get from our experiments can be put into those models. So basically, what we do in the lab can help us get a better picture of what's happening out there in the interstellar medium. Okay, so I've told you a lot of stuff today, and I don't expect you to remember every single detail, and it's not important for you to remember what my results are. You can always look them up. There will be publications soon. But I want you to take home these 4 messages. The first is that the interstellar medium is not empty, but there's a complex chemistry that takes place in spite of the harsh conditions. And then that there are a family of organic molecules called PAHs. And these PAHs are molecules you're very familiar with. Every time you look at your burnt toast, think of these molecules. And they potentially play an important role in bringing about the chemistry of the interstellar medium. And then we can study the interaction of PAHs with hydrogen atoms and deuterium atoms in the laboratory using a variety of techniques. So, you can do astronomy sitting in your lab. And then laboratory astrophysics is a really interesting interdisciplinary field. It has a little bit of everything. So if you're like me, who likes physics, who also likes astronomy, who likes a little bit of chemistry, and also wants to travel around, do stuff, then laboratory astrophysics is a great field because it just has the best of everything, I think. Yep, and I have a small promotional video for laboratory astrophysics. Again, I don't think the one that I've embedded in the presentation will work. So I'm going to again switch screens if I can find that out. Whoop. Yeah, sorry. I can't find my Zoom screen for some reason.
It's you can minimize your window. There should be an exit full view. You can no.
I've minimized all my windows, but okay, yeah. Okay, I got it.
Okay.
Yeah, sorry. So I'm going to share my screen again with the video. Okay, can you see the video now?
Yes, Rijutha.
Yes, Rijutha. Yeah.
Okay.
Hello, my name is Frederick, and I'm a PhD student working here at the Surface Dynamics Laboratory. At SDL, we work with surface-sensitive experimental techniques which require low pressures and precise control over the environment. Here I am, starting up an experiment with a colleague. The goal is to put atomic hydrogen and carbonaceous molecules onto a surface and let them react. Several steps of heating, cooling, and positioning of the surface must be completed in order to consistently produce valid data. Some measurements may take hours to complete, but each data point brings new and exciting information. A lot of different components are needed to make everything work, and when they break, we of course have to fix them. This is done with very clean tools and gloves to make sure no dust or other contaminants enter the vacuum chambers. Here I am, spot welding one of our sample surfaces tightly onto a sample holder that goes into the vacuum chambers. The surface shown here is graphite, which represents dust grains from interstellar space. At group meetings, we discuss what we have done throughout the week, and sometimes we present some of the recent data. Yes, of course, not everything is done in the lab. We also have to analyze the data or run simulations, which is usually done in the office. To examine large amounts of datasets, we use different programming languages to write codes that can help us efficiently analyze the data. Here, for instance, I'm trying to fit the peak desorption temperature for several measurements at once. These are some of the things I enjoy about being a PhD student working in the lab. Not only do you get to do frontline research, you also get the learning experience from hands-on work you do yourselves to fix the equipment. And you get the excitement from writing a working script that can be used to control the system more efficiently. Sounds interesting, right? Then maybe experimental physics is something for you.
Okay, going back to sharing my screen. Okay, so I just wanted to let you know that please feel free to write to me. This is my official email ID. You can ask me about life in Denmark, what did I do during my PhD, more about my research, or if you want to discuss about some of the results I presented today. How did I end up doing laboratory astrophysics? How small is this? Is the Little Mermaid? Are there more pigs in Denmark than people? Yes. So any such questions you can write to me if you don't get a chance to ask me today. Thank you for your attention. This is my first really long talk. I typically give like 15-minute talks or 20-minute talks. So this has been, I hope it was worth your time. And I want to thank all my group members, like former, current, because I've not only presented their data, but I've got a lot of support from them in the last 3 years. Especially when you are in a different country and an international researcher, they've been a great support for me. So thanks to them and former group members and my collaborators, especially the theory collaborators whose work I've also presented today. Again, thank you for your attention.
We will have the Q&A session now. You guys can post your questions on the chat box of Zoom or the YouTube live stream if you haven't already. And I request Shivani and Agnes to please take over.
Hello, good evening all. So the first question is from Aarti. It says, is there a reason for choosing symmetric PAH molecules?
Okay, that's a great question. So this field, if I can somehow, yeah. Let's go to the coronine. Yeah, the symmetric molecule in the middle. So coronine is considered a model PAH. And historically, people started doing research on coronine because it's kind of an analog for graphene. So if you repeat coronine over and over again, you get a graphene sheet. Except for the hydrogens, of course. So for theoreticians, it's difficult to work with an infinite dimension, infinite sheet of graphene, which is why they started using coronine as a model for making calculations on graphene, which is why historically, I think people started working with coronine. And then, of course, with pentacene, it is a symmetric molecule, but it's not as symmetric as coronine. So I think that's a move ahead.
Okay, thank you. The second question is from Aarti. What happens with change in the positioning of the oxygen molecules on the pH molecule you mentioned?
Okay, so this is a particular PAH where the oxygen atoms are on the central ring, and we are in the process of studying molecules which have oxygen atoms elsewhere. I would expect the sequence in which the hydrogen atom adds to be different. I did not talk about the sequence of hydrogenation in this talk, but it's quite important, knowing where the first hydrogen atom attacks, where the second one goes, where the third one goes. So I would expect a change in how the sequence of hydrogenation is, and then how the shape of the molecule changes. And once you have the shape of the molecule changing, I'm sure the sequence is affected by it. So that we need more experiments to definitely say that.
Okay, thank you. Next question, I think Arun sir posted one question in the chat box. It says, do the simulations allow you to check the effect of gravity on the molecule, like the formation or the dissociation, far away from any gravitational source it should be with zero gravity environment? And how sensitive will be the results, zero gravity results be?
Okay, so yes, we don't, in the simulations, we don't take gravity into effect. Often, so quantum chemical calculations are often done even, without considering a surface on which the molecules are. So they're done for like free gas phase PAHs. So even doing calculations by adding a surface is like one step higher. And often our theoretical colleagues complain about it. So I don't think, these calculations are pretty expensive in terms of, so in theoretical chemistry, it's always considered in terms of how expensive a calculation is. So they're typically done for gas phase isolated PAHs far away from the influence of anything.
Okay, thank you. I think that's it with the questions for today.
I think there is another question. Yeah, you've taken up this, right? From Arun sir? There's a question from Arun sir.
Yeah, yes, I've taken up that.
So anybody else, if you have any questions, you can unmute and ask.
I think Suraj has a question in the YouTube chat section.
Yeah, I think somebody is taking up questions from YouTube. Can you come in, Vikrant?
Shivani here.
Shivani, okay.
So, good evening, everyone. So, first of all, I just want to say there are less questions, but a lot of praises in YouTube. So, everyone really loved the talk. And so, the first question is by Elizabeth Meghna, and she asks, "What is the boundary of ISM?"
Sorry, I didn't get that.
What is the boundary of ISM?
What is the boundary of the ISM? Okay, I have actually not thought about this, but I guess it's wherever, right? Like whatever the boundary of the universe is, I guess, because it's like you have the interstellar medium, which is within a galaxy, and then you have the intergalactic medium, which is between galaxies. So I would say interstellar medium, like every galaxy would have its interstellar medium, and you could say the galaxy is the boundary, whatever the boundary of the galaxy is. And there's the intergalactic medium, and whatever the boundary of the universe is, that is the boundary of the galactic medium.
Okay, so the second question is by Suraj sir, and he asks, what are the other peaks present in the Mars graph, those which don't correspond to the coronae?
Yeah, thank you for asking that question. I can use maybe this as an example. Okay, so Coronine has a mass of 300. And then you have a peak at 301, a smaller peak, and then another smaller peak at 302. So the peaks at 301 and 302 are because of the presence of the carbon-13 isotope in the molecule. So if you actually take a ratio of the yield of the 300 peak and the 301 peak, it sort of matches with the isotope ratio you would expect, the C12 or 12C, 13C ratio that you expect. The masses below 300 are because, so in a mass spectrometer, how do you detect these molecules? It's by ionization. So like I told you, you can't do anything with a neutral molecule. You have to ionize it in order to study it. So when you ionize these molecules, they tend to lose a hydrogen or 2 hydrogens or 3 hydrogens, and that's why you see masses 300. So these correspond to a loss of hydrogen atoms in the mass spectrometer.
And there is one more question by Suraj sir. So he asked, there was evidence of higher reactivity for the pH with some concativity. So how about buckyballs?
Yes. So we are studying buckyballs or fullerenes. So for those of you who aren't familiar, buckyballs are like football-shaped molecules containing carbon atoms. They only contain carbon atoms. And there's this molecule that I showed you, corannuline. If you actually, corannuline can be considered as a fragment of C60. That is, C60 is like a football-shaped molecule, and corannuline is a fragment of that, which is why it's bowl-shaped. So C60 is like a completely spherical molecule, and we are studying the interaction of C60 with hydrogen atoms, and there's actually so there are papers in literature which kind of say that these molecules, PAHs, when they lose hydrogen, can actually curl up to form buckyballs. So, I mean, this is the examples I have here are very small PAHs, but if you had a bigger PAH, say like 100 atom PAH, then it could lose its hydrogen atoms and then curl up to form a buckyball. And that's how, so fullerenes have been detected in the interstellar medium. And this has been proposed as a formation route for fullerenes.
So that's it for the questions from the YouTube live. Thank you.
On behalf of Physeeksee and the PG Department of Physics, St. Joseph's College, let me extend a very hearty vote of thanks to Ms. Rijutha for sharing with us your work. I'm sure everyone found the lecture very informative and interesting. So this marks the beginning of the activities of Physeeksee 2020-21. First and foremost, I'd like to express my heartfelt gratitude again to Ms. Rijutha Jaganathan for graciously accepting to deliver the lecture today amidst her busy schedule. Next, I'd like to thank Dr. Melvin Colasso for his kind words and for being here on such short notice. An event like this does not happen overnight. The wheels start rolling weeks before the event. It requires meticulous planning and a bird's eye for details. We've been fortunate enough to have both Dr. Arun Tampan and Professor Parul Goel backing us up along every step of the way. Thank you, sir and ma'am, for all the efforts you've taken. Hope we haven't let you down. Hosting online events is no piece of cake. I thank Karan, Vikrant, Shivani, and Agnes for carrying out their responsibilities behind the curtain wonderfully. Last but not least, I thank each and everyone who turned up for the lecture today, faculty, students, alumni, everyone, for being patient throughout. Your participation is testament to the fact that curiosity is not dead. We hope to see you all again for our future events. Keep an eye out for our posts and updates. Thank you and have a nice evening.
Aarti, we have a question in the Zoom section. Is it fine if you take it?
Yes, of course. Go ahead.
So Rijutha, there's a question on the Zoom chat. Sanath asks, how do the current model explain the variation in H2 formation, if any, near the interface regions of MCR and PDRs?
Sorry, what is an MCR?
Sanath, you can unmute yourself and ask directly.
Molecular cloud region, okay. How does the current model explain variations? There are different models. So the thing is, there is no consensus. So a lot of people believe that PAHs play an important role, but then there are people who would say that if you add extra hydrogen atoms to a PAH, it becomes unstable, or it can be even more easily destroyed than a PAH. And then there are, of course, like I've only spoken about neutral PAHs today. There are, of course, PAH anions, PAH cations, and then there are people who have studied this as well. So if you do a quick Google search on like a PDR model, you will see that in a PDR, there are different regions where, there are regions where there are neutral PAHs, there are cationic PAHs, anionic PAHs. And then these different types of PAHs have different reaction rates or the way they interact with hydrogen. And so most current models have like a mixture of PAHs to explain the observed abundances of molecular hydrogen. And then, of course, there's always, okay, do we have more of anions and cations, or do we have more of neutrals? And this is a debate that keeps going on. So there will be people who will say, no, there can't be neutral PAHs, because if they're superhydrogenated and they're irradiated with UV, they will just break apart. So you will find a lot of debate in the community about this.
All right, I think it was a wonderful evening, Rijutha, having you here with us. Though you couldn't see expressions on people's face, I mean, that's the downside of it.
Yeah. So I didn't know if I was really getting through or not, or people were snoozing or.
No, you were absolutely. I think you were talking at a level that everybody could understand.
Okay.
Thank you, Rijutha.
And thank you for this really great opportunity. I've never shared my research work in so much detail before. So thank you.
It was largely to motivate our students to do research. So we hope it pays.
Yeah, I hope the videos sort of helped. Like they could see what our lab is like and what we do on a daily basis.
Yeah.
I mean, research doesn't have to be just sitting and reading papers, which is kind of what we think it is when we do our masters.
Absolutely, yeah. I mean, they could see the experimental part of research as well. So.
Yeah.
Great. All right, so I think if we don't have any more questions, then probably we can bring the session to a close. Yeah.
Okay.
So Thanks.
Bye. Bye. Bye, Ashwin.
See you, sir.
Bye.
Ashwin,
It was a very nice talk,
we'll
Rijutha.
hear from you soon.
Yeah.
Yeah, Ashwin, you're next.
Yes.
This is like, you reach at the age of 25, 26, you go to weddings and your relatives are like, you're next.
Yeah, it's like that.
Yeah. But thankfully it is not.
In this community.
Yeah, but thankfully it is not, Ashwin. I mean,
Yeah.
Next for the talk.
Yeah, people here don't know I like to talk a lot, so they would probably run away.
no, they already have me.
But Ashwin, the best part is here we can just mute you or like.
But why would you want to do that? Spend all that time to call me and then mute me.
Do that.
Yeah.